Now we have spent quite a bit of amount time on creep. Now let us focus what is a shrinkage. Shrinkage, as the name indicates, the volumetric contraction is going to happen. So, shrinkage of the concrete is defined as the reduction in volume of concrete due to loss of moisture. So, that is what it is given here, and shrinkage strain also is going to evolve over a period of time. Okay. And typically it is caused by the drying process and is resisted by the stiffness of the concrete. It's basically the shrinkage will not create cracking when you restrain the shrinkage, because most of the time the elements will be connected with other elements. So, when the element wants to shrink, it will not be allowed to shrink. So, it is a restraint to the shrinkage that will induce tensile stresses, and it will induce this kind of cracks. So, when there is no restraint, concrete can shrink or expand freely, then there will not be any crack. Okay. So, the factors that affect the creep also affects the shrinkage, and shrinkage strains are typically independent of the stress conditions in the concrete, and also the shrinkage is largely reversible. That means when the temperature becomes dry or wet, or the climate becomes dry or wet, it will cause alternative volume changes in the concrete. So, they are largely reversible in nature. So, that is the reason in the initial period we need to cure the concrete really well, so that the escape of moisture does not happen at the early ages, especially that is the reason at least up to 7 days we need to cure the concrete really well, but most of this shrinkage related problem happens at the early age. So, if you cure the concrete really well, then the shrinkage strains can be reduced to a large extent. And these are the type of this kind of cracks that you get. These are all from early age shrinkage cracks in the concrete. These are the slab on grade cracks. And also to account for this volumetric changes, typically we put expansion joint or these kind of joints. We cut the joint and we put some reinforcement, right? But you have to account for that temperature change that is happening to account for this shrinkage as well as volumetric changes that are happening. Right. So, now total shrinkage of concrete again depends upon the constituents of the concrete, size of the member, and also the environmental condition. These are the important factors. Now, we also have carbonation shrinkage. However, typically the shrinkage induced from carbonation is basically the CO2 can penetrate inside the concrete, and they can react with calcium hydroxides which are in the system. Then they can form calcium carbonate. This creates some shrinkage issues, but typically they are not they are minimal unless you are dealing with the system in the CO2 rich environment. Then we need to account for that as well, but typically we account for drying shrinkage and autogenous shrinkage. Now, what is drying shrinkage? This is a water loss that is happening due to environment that is absorbing this moisture from the concrete system. And autogenous shrinkage is the shrinkage or water loss that is happening because of the hydration process, because of the chemical reaction, right. Both are important. Now, from calculations point of view, we club all of the two of them together and call them as a shrinkage strain. So, but typically the drying shrinkage is much higher than that of autogenous shrinkage, typically an order of magnitude higher. Drying shrinkage is much higher than that of autogenous shrinkage. Right. Now, how does the code addresses? Again, we have discussed the total shrinkage of concrete. It depends upon the constituents of concrete, size of the member, and environmental conditions. For a particular humidity and temperature, the total shrinkage of the concrete is most influenced by total amount of water present in the concrete at the time of mixing, and to a lesser extent by cement condensation. Predominantly, it is the unutilized water that is in the system that will create shrinkage strains. For design code clause 6.241, it allows us to use 0.0003 as a strain, but you can see the ACI accounts for about more than 0.0008. Again, that depends upon the climatic condition and the temperature profile that you have or in your country. But in India, typically tropical weather, most of the regions, so code asks you to use about 0.0003 in our calculations. Now, how to estimate that? Again, we have studied this. Higher the water, more will be the shrinkage that you can see here. Water is plotted in the x-axis and drying shrinkage is plotted in the y-axis. You can see here that if you are using more water in the system, then your shrinkage can go as high as 1200 millions, right. So, that you can see, you can divide by the million to get the exact unit, right. And also type of cement. So, and type of aggregate. You have large aggregates in the system, less cement paste, then lesser will be the shrinkage. And if you have more stiffer system, then again less will be the shrinkage. And the best way to also is reduce this using mineral admixture, that will help in increasing the microstructure and reducing the shrinkage as well. And another way of improving or reducing the shrinkage is by putting a reinforcement on the compression side. Typically, drying shrinkage of the reinforced concrete is expected to be less than that of plain concrete. But reinforced concrete, because the reinforcement will restrain that free shrinkage that is possible in a concrete system, but it cannot completely prevent the drying shrinkage. Okay. And also you can see clearly that higher the water in the system, higher will be your drying shrinkage. The one way to reduce the effect of creep and shrinkage is to use low water to cement ratio in your design, but from workability point of view, you can always use super plasticizers in your mixed design. Okay, now drying shrinkage, as we have said, it is a migration of water through hardened concrete, and code, how does it address this? Again, it varies with respect to time, right. And you take the final value, this is the final value suggested by code, right. Then depending upon at what time that I am doing calculations, I need to apply some reduction factor, right, and then some H0, the notional size coefficient factor. So, now let us see what is this beta ds reduction factor is. It depends upon time of curing, the difference in time of curing to time at which you are doing the calculation, and also it is function of your H0, right. So, again, higher your H0 value, lesser will be your creep. So, that is why it is in the denominator. Okay. T is the age of concrete at the instant of consideration days, and Ts is the age of concrete at the beginning of drying shrinkage in days. That means, let us say you water cure the concrete cubes for 14 days from the time of casting. So, Ts will become 14. Okay. So, that means when you stop the curing, water curing, and you take out the samples, that is the time from the day of casting, that will become your Ts. Okay. If you are doing water curing for, let us say 14 days, then Ts will be equal to 14 days, right. So, H0 is a notional size coefficient that we talked about, and use a perimeter. Kh is a coefficient that depends upon the notional size H0, and you can see here, higher the H0, lesser will be your Kh value, okay, or lower the H0, higher will be Kh, means higher will be the shrinkage strength, right. So, if you have larger surface area, more will be the shrinkage and creep. So, but that larger surface area means lower H0, that is what it is, right. So, you can do the interpolations. And then drying shrinkage value, the code is also giving you what should be the final value that we need to consider in our design. This final value is given in the code for different concrete grade. For example, if I am using 50 megapascal concrete, and let us say my location is in Hyderabad with a dry condition and 50% of relative humidity. So, the final value that I need to 50 means 420 strain. Now, that again I have to multiply this with Kh, and I multiply with beta factor, beta ds factor. So, this is the final value, maximum value that it is possible. Then I need to knock it down by Kh factor and beta ds factor. So, that is what we do. Then autogenous shrinkage, as you know, it is because of the chemical reaction. It develops during the hardening of the concrete, major part of the early days of casting, right. And when external water is available, or when you are water cure it, autogenous shrinkage typically does not occur, and autogenous shrinkage increases with decrease in water to cement ratio and with an increase in fineness and amount of cementitious material. More the cementitious material, more the fine content, higher will be your autogenous shrinkage. So, this is the variations of your shrinkage, as you all know. But as I have explained you, autogenous shrinkage is typically much lower than that of drying shrinkage for a typical normal strength concrete. But if you are using high strength concrete with lot of cementitious material, then it can also become comparable to that of drying shrinkage. So, that is what it is, right. Now, that again, just like what we do for drying shrinkage, this is the final value, then you reduce it by this reduction factor. Now, how to get the reduction factor value? which is again depending upon what time that you are doing the calculation, that the code is giving you some empirical equations for taking into account. So, this is nothing but a reduction factor. T is, let us say T is in days, 1 year means T will be 365 days. So, you put 365, calculate your beta AS factor and then multiply with the epsilon CA that is suggested by the code, then you get your epsilon CA at time T equal to 365 days. Right. So, these are the table. So, epsilon CA is given by these values. Now, again you can see here, with increase in the strength of the concrete, epsilon CA will increase as is expected. Higher the strength of the concrete, higher will be your cementitious content, higher will be the reaction and more will be the autogenous shrinkage. So, that is what, but you can see here this value is like roughly about 1/4 or 1/5 to that of what you get for your drying shrinkage. So, it is only about 20-25% of your total drying shrinkage. So, it is not a major component. Right. Temperature effect, again we have to be very careful, especially in pre-stress system when you go for a long span elements, concrete, if you are not careful, concrete can expand with increase in temperature and can contract due to the decrease in temperature. To accommodate that, typically we use this kind of a expansion joint, right, especially in bridges. We have to, now we have something called deck continuity. If at all you are doing deck continuity designs, then you need to provide enough reinforcement so that even if it is cracking, the crack width not be very significant. Okay, that we have to, in design we have to account for that. Okay. So, typically to limit the temperature stresses, expansion joints like this are provided. Temperature stresses develop and due to the temperature gradient in structural elements, especially which are exposed to the external weather, they tend to have more temperature effect. A nominal reinforcement is usually provided for addressing the temperature effects, and depending upon the type of aggregates that you have, typically if you have siliceous aggregates in the system, they will have higher coefficient of thermal expansion. That again depending upon, because aggregates constitute 70% of the volume of concrete. So, if you are using siliceous aggregate which is going to have higher coefficient of thermal expansion, then your temperature stresses also will be higher, which need to be accounted in our design. Right. So, with that let us summarize what we have discussed in this part of the module. We have spent quite a bit of time on understanding the stress strain curve behavior of concrete, what are the various design stress strain curve that are proposed by IS 456 and IRC 112. We spent a lot of time on creep and their effect on concrete and how the IRC and IS codes accounts for the creep effects. We also talked about shrinkage and their effect on the concrete. And we also spent quite a bit of time on how the code is actually calculating the strain from creep coefficient, and also we looked at the shrinkage strain, how to calculate the drying shrinkage strain and how to calculate the autogenous shrinkage strain. So, with that we are completing this part of the module. Thank you everyone for your patient listening. Looking forward to the other parts of the module. Thank you.